Okay, so still 21.3. The sections in chapter 21 are giants, so bear with us. So this is going to be the directed aldol, and honestly, this is the way most aldol additions, most enolate chemistry is done this way. Okay, the simple aldol in the last video, I didn't want to say it in that video because I didn't want you to stop looking at it. That isn't all that effective. There's a lot of limitations on the simple aldol reaction. On a directed aldol, there are no such limitations. This works really well. So again, it's an aldol, so we're going to make an enolate. Could be an enolate of any sort of carbonyl compound in this case. And then we're going to add that to either an aldehyde or a ketone. Okay, so what makes it directed? Well, we're going to use a strong base. So we are going to let's use a real example. Let's use ethyl acetate, and let's say we want to make we want to have ethyl acetate add into all right. So there's the molecule we want to make. How do you do that? So in the simple aldol, if we simply took cyclohexanone and ethyl acetate and NaOH, what happens? So we take cyclohexanone, ethyl acetate, hydroxide. Probably the hydroxide just adds in here, kicks out ethyl acetate. Probably the cyclohexanone doesn't do anything. It might aldol on its own. Right? There's nothing stopping cyclohexanol from attacking it, making an enolate. Right? You can deprotonate either of these places. Cyclohexanone is a ketone. It's a little more acidic than an ester. So it either is not going to do anything or it's going to aldol on itself, and then we'll also get ethanol and acetic acid. In other words, we can't make this product doing a simple sort of aldol reaction. And so what we do, step one in a directed aldol, is make enolate quantitatively. And really this is going to require LDA. Okay, so ethyl acetate. Now, LDA is a very strong base, and it's bulky. It's not very nucleophilic. It's not going to add in here to the carbonyl. So it's going to take the proton. And you typically do this cold, so minus 78 degrees C or so that the ester enolate doesn't attack itself. The ester enolate attacking itself would be a Claisen reaction, and that's section 4. So if you want to go look at that, ester enolates can attack esters, but it's slow. And so if you do this reaction at minus 78, the acid-base reaction happens, and you go all the way. So I've drawn this as an equilibrium. This just becomes, we make ester enolate. And then add the electrophile. Right? So you never had cyclohexanone in the presence of the base. You make the enolate, then you add the electrophile, and so now we have this reaction. Negative cyclohexanone there's the addition alkoxide. And again, so we make the enolate completely. We have a flask full of enolate. And then there's no electrophile in there. There's nothing for this thing to do. And enolates are perfectly stable that way. If you don't give them an acidic proton or an electrophile, they will sit there forever. Right? It's hard to keep water out. So the enolate will attack water. On Earth, it's hard to keep water out of that. Okay, so then we add the electrophile. Enolate, the nucleophilic enolate attacks the electrophile, we get this. And then, if we want the addition product, gently protonate. What do I mean by gentle? Okay, it doesn't matter how fast you squeeze it in. You want to keep this cold and use a weak acid. That's what I mean by gentle. You don't want to heat this up, so you want to do this whole reaction cold at minus 78, certainly below 0, and then use a weak acid. It could be water. Sodium bicarbonate's nice because it kind of buffers it. If we don't do that, if we treat this thing hard, so heat, and heat in this case might not mean heat, it might mean room temperature, if it's just like 25 degrees. So strong acid. So and the other thing to keep in mind, you're neutralizing, this is a strong base. If I put acid in there, I'm going to generate heat. So I might think I'm keeping it cold, but I'm not really keeping it cold. So let's say this is 50 degrees C and HCl. Well, you're really likely to do an elimination at that point. So you get an elimination. Or aqueous acid, heat, you've got an ester there, you can hydrolyze it. Or you can do both. All right, so these directed aldols, this is, like I said, this is the way people do enolate chemistry. Step 1, make the enolate. There. I treat my enolizable compound with strong base. Bang, I get an enolate. I keep it cold. I very slowly add the electrophile. I get my addition product. And then very gently, I warm it up and protonate the O-. Okay? Maybe I want hydrolysis, maybe I want elimination, in which case then I can blow it off, or I can, hit it hard. But that's the directed aldol, and that's the way you'll probably do most of the aldol problems in this section.